Have you ever really stopped to think about how a device that only gets to on and off can somehow show you a movie, play your favorite song, or connect you to literally billions of people? It feels like it should be impossible, right? But it all comes down to a very simple but incredibly powerful secret language. So let's pull back the curtain and figure out how computers really talk.
This right here, this is the big question. How in the world do we get from a tiny electrical switch being flipped on or off, a 1 or a 0, to the unbelievably rich, complex digital world we all live in? Well, that's the journey we're going on today. We're going to build it all from the ground up, one switch at a time. So here's our game plan. We'll start by learning the computer's secret language. Then we'll find a way for us humans to actually read it without going crazy. After that, we'll see how it does math, learn how it paints pictures and creates sound, and finally, figure out how it shrinks all that information down so it fits on your phone.
Okay, part 1. To understand how computers work their magic, we have got to learn the language they think in. And believe me, it's way, way simpler than any language you've ever tried to learn in school. You know, we live in a base 10 world. We've got 10 fingers, so it just makes sense that we came up with 10 digits to count with, 0 through 9. But a computer? It doesn't have fingers. It has millions of tiny electronic switches, and a switch can only be in one of two states, off or on. So its language is base 2, or what we call binary. It uses just 2 digits, 0 for off and 1 for on. That's it.
Now, every single one of those zeros and ones is called a bit. Think of a bit as the absolute smallest atom of digital information. And when you group 8 of those bits together, you get what's called a byte. So if a bit is like a single letter, a byte is like a small word. And with just these simple building blocks, you can build literally anything.
All right, so computers are perfectly happy crunching away on these long, long strings of ones and zeros. But for us humans, trying to read that stuff is, well, it's a total nightmare. So we needed a better way to communicate with our machines. I mean, seriously, can you imagine trying to type out 1,000 ones and zeros without making a single typo? It would be incredibly slow, and you're almost guaranteed to mess it up. Programmers and engineers knew right away they needed a more compact, human-friendly way to write out all this binary data. And the solution they came up with is just brilliant. It's called hexadecimal. It's a base 16 system. So it uses the 10 digits we already know, 0 through 9, and then it just borrows the letters A through F to represent the values 10 through 15. And here's the magic. A single hexadecimal digit can represent a chunk of 4 binary digits perfectly. It's the ultimate shorthand. And you've definitely seen hexadecimal out in the wild, even if you didn't know what it was called. It's used to define the exact shade of blue or red in web design. It's in those weird error codes your computer sometimes spits out. And it's absolutely fundamental to how the internet works, like in MAC addresses that identify your device or the IPv6 addresses that route all the data across the globe. And here's a perfect real-world example. Every single device connected to your Wi-Fi, your phone, your laptop, your smart fridge, has a unique ID called a MAC address. That code, written in hex, is how your router knows exactly where to send that funny @ video you're trying to watch. Okay, so we've got a language, we've got a shorthand to make it readable. The next big jump is, how can a bunch of simple on-off switches actually do math? The answer is surprisingly elegant. These are literally the only 4 rules you need to know to do addition in binary. Now, 3 of them are exactly what you'd expect. The only one that looks a little weird is the last one. 1 + 1 = 1, 0. Why? Well, because there's no digit for 2 in binary. So instead, you write down a 0 and you carry the 1, just like when you add 9 + 1 in our system. Let's see it in action. Say we want to add 5 and 7. In binary, that's 0101 + 0111. You just apply those simple rules, column by column, from right to left, carrying the 1 when you need to. And the result you get? 1100, which is exactly how a computer writes the number 12. Every complex calculation your computer does boils down to this, just happening millions of times a second. But there is a limit. See, a computer sets aside a fixed amount of space, say 8 bits, to store a number. If you do a calculation and the answer is too big to fit into those 8 bits, you get what's called an overflow error. The computer literally runs out of room to write down the answer, and that can cause programs to get weird or even crash. So, computers can count, but how do we get from just counting to actually creating things? This is the part where we connect all the dots, and we see how these abstract numbers become the real things we see and hear every day. This is really the big secret, the main takeaway. The words you're reading right now, the colors on the screen, the sound of my voice. To the computer, it's all just a massive, massive list of numbers. A computer doesn't know what a picture is. It just knows the sequence of numbers that represents that picture.
Let's start with text. That's the easiest one. How does computer know what the letter A is? It doesn't. It just follows a standard code, like ASCII, where a specific number, a specific pattern of bits, has been assigned to represent the letter A. So when you type, you're really just telling the computer to store a bunch of numbers.
What about images? Well, they're built from a grid of tiny little dots called pixels, and each one of those pixels is given a binary number that tells it exactly what color it should be. For a simple black and white image, you could just use a 1 for black and a 0 for white. If you want color, you just need a longer binary number for each pixel to describe all the different shades.
Here's exactly what that looks like at the most basic level. This is a bitmap of the letter H. You can literally see how a simple grid of ones and zeros creates a shape we can recognize. Now just imagine that grid being millions of pixels wide, with each pixel having thousands of possible colors. And that's your high-definition photo. And finally, sound. Sound is an analog wave, right? It's smooth and continuous. To turn it into something a computer can understand, the computer takes thousands of tiny snapshots or samples every single second. It measures the height of the sound wave at that exact moment and gives it a binary number. Then to play it back, it just reads all those numbers in order and recreates the wave. Okay, so we've translated our world into numbers, but this creates a whole new problem. The files are huge. A few minutes of good quality audio or one detailed photo can be made up of millions and millions of bytes. So how do we manage all of that data? The answer is compression, and there are two main types. Lossless compression is like a perfect zip file. It finds clever patterns to pack the data smaller, but when you unzip it, every single bit comes back exactly as it was. This is essential for things like text files. Then there's lossy compression. This is what JPEGs and MP3s use. It actually throws away some data forever, but it's data that our eyes and ears aren't very likely to notice anyway, and in exchange, you get a much, much smaller file. And that's the whole story. From one simple on or off state, we build numbers. With numbers, we learn to do math. And by giving numbers a meaning, by assigning them to letters and pixels and sound waves, we can represent our entire reality in a digital form. It's an incredible system, really, all built on the simplest possible foundation. Which leaves us with one final big question to think about. If a computer only ever sees numbers, codes for colors, sounds, and letters, what does it fundamentally lack? What's the one thing it will never truly understand about the world it represents so perfectly?